Hi there, physics besties. We're back again, this time talking about rotational inertia. We learned from Schall's theorem that we can divide up the angular momentum of a system in terms of the angular momentum due to the translation of the center of mass, plus the angular rotation due to the rotation of an extended object about the center of mass. It's the second piece that we want to focus on, the angular momentum of an object when it rotates about a fixed point. And what we're going to learn in talking about this is we can characterize the rotation, angular momentum, in terms of an angular velocity, omega, and a rotational inertia, sometimes also called a moment of inertia. So the system that we'll use to develop this idea is this, a rotating dumbbell. And this purple point indicates a fixed point. So these two dumbbells are going to rotate about this point in a circle, like so. Okay. So the big mass M2 goes around in a circle, little mass M1 goes around in a circle. This point never moves, that purple point. So let's define some of the parameters of the system, and we'll treat each of these two objects as point particles connected by a massless but rigid rod. So the shape of this object doesn't change, it just rotates. We'll need some other parameters to characterize the system. The first is that we'll talk about a position vector, R1, out to mass 1, and a position vector, R2, out to mass 2. And I'm going to get rid of some of these decorations for now. Now that we understand this system is rotating, I don't think we need to have all of this to distract us. Okay, great. In addition to these two position vectors, there's going to be a linear momentum for each of these particles, and that linear momentum will be tangential to the trajectory. And since we know that trajectories are circular, we know that in this case, the two momenta will be perpendicular to their position vectors. Okay, great. So how do we write down the angular momentum of this system? Well, we can sum up the vector angular momenta for each of these two particles, L1 and L2. First of all, let's just figure out what direction these angular momenta are pointing. So if we do the right-hand rule of R1 cross P1, that's going to give us an angular momentum vector that's out of the page. Let's define out of the page as the plus z direction. In that case, both L1 and L2 point out of page. Okay, so that's the plus z hat direction. Very good. And what are L1 and L2? Well, L1 is R1 cross P1, and L2 is R2 cross P2. So we just need a way to write out each of those terms. So I'm going to kind of move over to the right here, and we'll solve L1 separately and L2 separately, and then we'll come back on the left-hand side and combine them. Okay. So we already know the direction, so all we really need at this point is to figure out the magnitude. Okay, so the magnitude of that cross product is mag R1, mag P1 times the sine of the angle in between them, but our position vector is perpendicular to our momentum vector. P1, as you'll recall, is the mass times the velocity, and the magnitude would be, the magnitude of the momentum is the mass times the speed, and the speed for this circular motion is r times omega. So we have here two factors of r, 1, 2, one factor of mass, and one factor of omega. So we have m1 times r1 squared times omega times the sine of 90, which is unity. Okay, and you can do the same thing for the magnitude of L2. It's mag R2 cross P2. Everything's the same in structure, and except we have subscripts 2, m2 r2 squared times omega. Okay. So if we come back to an expression for the angular momentum of our system, what we can see is we're going to have m1r1 squared omega in the plus z hat direction for the first angular momentum, plus the same thing for mass 2 and r2, also in the plus z hat direction. So at the end of the day, we'll have m1r1 squared plus m2r2 squared if we factor out that omega, all in the z hat direction. Okay, so notice what we have on this right-hand side. Okay, if we look at the magnitude of this momentum, it's equal to mass times radius squared summed over all the particles times the angular velocity of the system. This term in parentheses depends only on the shape of the system, right? What are the masses and where are they relative to the origin? So this depends only on the shape of system. And by shape, I mean the masses and their relative configurations. Okay, so we can group that into a quantity called the rotational inertia. That quantity is sometimes called the moment of inertia. And what we're seeing here is that if we are rotating about some point, then we can define the angular momentum due to the rotation about that point as the product of a quantity that is determined by the shape of the object and the angular velocity of that object. Okay, so this term I is what we're going to call the rotational inertia. Okay, in general, you might have more than two particles. Okay, so we can write down the rotational inertia for more than two particles. So let's say you have n point particles. We can write down the rotational inertia as the sum of mr squared, okay, for each of these objects. And the sum goes from 1 to n. But there's a very important caveat here, okay? This Ri is the perpendicular distance between the object and the axis of rotation. What do I mean by perpendicular distance? Well, here we had the fact that the sine of the angle between r and p was 90, okay? So for example, let's say we have the following situation. We have an axis of rotation, like so. We'll call that the z hat direction. That's our axis of rotation. And let's put two particles out here. Let's have them both have the same mass, m. Let's then make our origin somewhere over here. And let's let the masses be equidistant from that axis of rotation. And let's have them rotate. We could make this actually a dumbbell, so they're connected by a thin massless rod. And they're rotating in the horizontal plane, like in the xy, or plane parallel to the xy plane, with an axis in the z direction. Well, we have position vectors out to each of these objects from the origin. Okay. But when we talk about the rotational inertia, we are not talking about those position vectors. We are talking about the perpendicular distance between each mass and the rotation axis. So that's the shortest distance between that point and the line of rotation. That's the r perpendicular. That's what we mean in this equation up above, right here. Okay. In other words, Ri perpendicular is not the magnitude of the position vector in general. It is the closest distance between the mass and the rotation axis. If the objects are planar, in other words, if all of the objects and the origin are in the same plane, and the origin represents the rotation axis, then our perpendicular is the same as the magnitude of the position vector. That's what we used already. In this problem, we've moved into a three-dimensional situation where we have an origin that's not in the same plane as the masses and their rotation. So then we have to focus on our perpendicular, which is different than the position vector. So let's compare the angular momentum and the linear momentum. Okay, so in the case of linear momentum, we're going to talk about terms and contrast and compare it with angular momentum. Okay, so in linear momentum, we have a momentum for the system, which is given by the mass of the system times the velocity of the center of mass, and that's a vector quantity. In angular rotation, due to the rotation of an object about an axis or about a fixed point, we just found that the angular velocity of a system is equal to I omega. And here we really only specified the magnitude. So let's take the magnitude in these cases and compare those. Okay, so the magnitude of the momentum is mass times linear speed. The magnitude of the angular momentum is a quantity that's kind of like mass, it's a rotational inertia, times an angular speed. Okay, so there's this interplay or this similarity between v, a speed, and omega, an angular speed. Okay, and then there's a relationship or an analogy to be drawn between m and I. Right, one way to write m is an inertia. It's a resistance to acceleration. Okay. I we can think of as a rotational inertia. It is a resistance to angular acceleration. Okay, and what you can see is that this rotational inertia, I, does not only depend on the mass, right? It depends on where the mass is. In other words, if you take this point particle and move it further from the rotation axis, it would be harder to get this system to spin, even if you don't change the actual mass of the system. Right? So the further you put mass from the desired rotation axis, the more effort it takes to spin, the more torque you need to change the angular momentum. So we're going to come back to this in future videos and work with angular momentum and the rotational inertia. But until next time, take care and be well.